All right, let's dive in. Today, we are going to pull back the curtain and decode the language that computers actually speak. We're talking about how machines really think in numbers. So, let's kick things off with a little puzzle. Think about the number 29. Simple, right? You and I, we know exactly what it means. But get this, to your computer, that number might as well be from another planet. It's completely foreign. So what's going on there? The answer, and it's surprisingly simple, is a language barrier. Yep, we just don't speak the same numerical language as our devices. And you know what? Cracking that code, that's the key to everything we're going to cover. Okay, so take a look at this. It really breaks down the two languages. On our side, we've got what's called decimal, or base 10. That's the stuff we use every day, the digits 0 through 9. But then you have the computer's language, binary, or base 2, and it's way simpler, using only 2 digits, 0 and 1. But hey, don't worry about it. By the time we're done here, you're going to be a fluent translator between these two worlds. Seriously, you'll know exactly how to speak the computer's native tongue. All right, first things first. We're diving into the most essential piece of the puzzle, translating our everyday numbers into the ones and zeros that computers actually get. Now, the rules for this are surprisingly simple, trust me. It's really just a process of dividing over and over again. You take your number, divide it by 2, and you hang on to the remainder. Then you take the result of that division and just do it again. You keep on going until you hit 0. That's it. Okay, so let's put this into practice. Remember our mystery number, 29? Let's walk through this whole process, step by step. All right, step 1, we take 29 and divide it by 2. That gives us 14 with a remainder of 1. Now that remainder, that 1, is super important. It becomes the very first digit of our binary number, all the way on the right. You can think of it like the ones place. It's what we call the least significant digit. See, now we just repeat the process. We take that result, 14, and divide it times by 2. That gives us 7 with a remainder of 0. So our next binary digit, moving to the left, is 0. Starting to see the pattern here? So we keep doing this all the way down until our result is 0. And what we're left with is this list of remainders we've been collecting. But here's the key, the one little trick you have to remember. You don't read them in the order you found them. Nope, you have to read them backwards, from the very last remainder you got all the way to the first. Okay, here's the whole thing laid out so you can see it all at once. If we follow those remainders from the bottom all the way to the top, starting with what we call the most significant digit, we get 1, 1, 1, 0, 1. And just like that, we've done it. Our number 29 in the language of a computer is 11101. We've cracked the code. But hold on a second. That's great and all, but communication is a two-way street, right? How can we be absolutely sure that 1110.1 actually means 29? Like, how does the computer translate it back to our language? Well, the good news is the reverse process is just as logical. It all comes down to something called positional value. Think about it. In our normal numbers, we have a ones place, a tens place, a hundreds place, and so on. Binary works the exact same way, but instead of powers of 10, everything is a power of 2. All we have to do is multiply each digit by its position's value and then add it all up. Let's break this down with our example. If we work from right to left, the positions are the ones place, the twos place, the 4s, 8s, and 16s. See, all powers of 2. We just multiply each binary digit by its value. So we've got a 1 in the 16s place, a 1 in the 8s place, and check this out, that 0 in the 2s place basically just turns that position off. It's like a switch. And now for the final step, we just add up all those results. So 16 plus 8 plus 4 plus 0 plus 1 gives us 29! Boom! It actually works. We've come full circle. The translation is 100% correct. So think about what we just did. We've mastered this core skill of translating between our language, decimal, and the computer's language, binary. And because of that, we can now use decimal as a kind of translation hub. It's like our universal go-between for other computer languages, like, say, octal, which is a base 8 system. The strategy here is a really simple two-step process. Just think of decimal as your universal translator. It doesn't matter what language you're starting with, octal, hexadecimal, whatever. You convert it to decimal first, and then from there, you can easily convert it to any other language you need. It's brilliant. Let's see exactly how this works with an example. Let's take the octal number 25. Okay, step 1 on the left. We convert it to decimal. Since it's base 8, we use powers of 8. That gives us 21. Easy enough. Now, for step 2, on the right, we just take that 21 and use the same division method we learned before to turn it into binary. And we get 10101. See? 2 simple steps and we've got our answer.
Okay, so you've got the fundamentals down. You know the long way to do it. But now it's time for the pro tips. Because, let's be honest, there are way faster ways to do this, and I'm about to show you how to translate like a total expert. So you can basically forget that whole 2-step process we just talked about. When you're going from binary to octal, there is this beautiful, elegant shortcut. All you do is group the binary digits into little sets of 3, and you start from the right. Just look at how this works. We take our binary number, 10101. We start from the right and group it into 3s. The first group is 101. The next is just 10, so we add a 0 in front to make it a full group, 010. Then you just convert each little group. 101 is 5 in decimal, 010 is 2. Put them together, and you get 25. How fast is that? No more long division or multiplication. It's so efficient.
And what's really cool is that this grouping idea is super versatile. It's not just for octal. For instance, if you want to convert to hexadecimal, which is base 16, you just group the binary digits by 4s instead of 3s. And it works in reverse too. Going from octal back to binary, just take each octal digit and turn it into its 3-digit binary version. It's this powerful, efficient pattern that saves so much time. So what does this all mean? It means you're not just someone who uses a computer anymore. You're a translator. You get it. You now understand the fundamental language that powers literally everything in our digital world. So that leaves just one last question. Now that you can speak the language, what are you going to tell the computer to do?